In the first video on sound waves, we introduced a sound wave as being a longitudinal wave created by vibrations. The particles that generate the wave vibrate in a direction that is parallel to the direction of the wave movement. This results in regions of compressions or high pressure and regions of refractions or low pressure. When the vibrations are periodic, it also produces a periodic variation in the pressure, which is given by the change in the pressure being equal to the product of the bulk modulus, the displacement amplitude, and the wave number multiplied by the cosine of the wave number with displacement and angular frequency with time. The maximum pressure change is equal to the amplitude of the pressure wave, which is the product of the bulk modulus, the displacement amplitude, and the wave number. Sound can also be described in terms of its intensity, which is defined as the power divided by the area which the power is distributed, or the power per unit area. The letter P, representing power, is different to the letter P used to represent the change in pressure, so the two shouldn't be confused. We've already introduced the concept of power in the energy and momentum chapter. Power is a rate of energy use and has a unit of joules per second, or the watt, while area has a unit of meters squared, so intensity has a unit of watts per meter squared. In terms of the sound pressure, it can be shown, but not here, that the intensity of the sound can be expressed as the square of the maximum change in pressure divided by twice the product of the density of the medium which the sound is traveling in with the speed of the sound wave. One of the best instruments for hearing sound is the human ear. It has a remarkable ability to hear a wide range of sound intensities. The faintest sound that the average person can hear at a frequency of 1000 Hz has a sound intensity of only 10 to the negative 12 watts per square meter. We call this the threshold of hearing. At the other extreme is the threshold of pain. This is when the sound intensity is so strong that it hurts our ear to listen to that sound. For the average person, this threshold is around 1 watt per square meter for a sound with a frequency of 1000 Hz. The ear has an amazing ability to hear sound in a wide range that covers 12 orders of magnitude. That's a range of over 1 trillion times. It would be very difficult to plot such a range on a graph, so sound is commonly expressed in a smaller, more convenient scale of the decibel. The decibel is a logarithmic unit used to express a ratio of two quantities of the same dimension. For sound, this quantity is sound intensity, I over I naught, where I is a reference level. The decibel scale has a unit of dB and the logarithm is to the base 10. Logarithmic scales are convenient when one of the numbers in the ratio is very large by many orders of magnitude compared to the other. When using the dB scale with sound, the scale is often referenced with respect to the threshold of hearing, which is 10 to the negative 12 watts per square meter. So what is the threshold of hearing equal to on the dB scale for sound? If we reference the threshold of hearing against itself, we get 10 times the log of 10 to the negative 12 over 10 to the negative 12. This gives us a value of 0 dB. What then is intensity corresponding to the threshold of pain in decibels? When the threshold of pain is taken as a ratio of the threshold of hearing, then the intensity level is 10 times the log of 1 over 10 to the negative 12. This gives a level of 120 dB. So using the dB scale, we've conveniently converted from a range of 10 to the 12, or a trillion, to a range of 120 for sound intensities between the threshold of hearing and the threshold of pain. So what is the change in dB when the sound doubles its intensity? When a sound doubles its intensity, this is equal to a change of 3 dBs. What about when the sound halves its intensity? When the sound intensity is halved, this is equal to a change of minus or negative 3 dBs. Here are a few common sounds and the typical intensity levels expressed in dBs. A whisper is around 30 dBs, while a normal conversation is between 50 to 60 dBs. So while the change is only 20 on the dB scale, This is an increase of 100 times in intensity amplitude of the sound from a whisper to a normal conversation. The loudness which we perceive sound depends on a number of factors, including our age, as well as the frequency of the sound as shown in this chart. This is due to our ear's ability to respond to the rate of vibrations from the sound. In general, we perceive sound of very low and very high frequencies to be less loud. In summary, sound intensity is related to sound pressure and is equal to the square of the maximum change in pressure divided by twice the product of the density of the sound medium with the sound speed in that medium. Because the human ear can pick up a very large sound range, it is convenient to use the logarithmic scale of the decibel, which is given by 10 times the log of the base 10 of the ratio of two sound intensities. Sound intensities on the dB scale is typically referenced against the intensity at the threshold of hearing, which is 10 to the negative 12 watts per square meter.